Have you ever stopped to think about how a soft, mushy piece of clay turns into something so hard it can last for thousands of years? You might think the real magic happens in the fiery kiln, but you'd be wrong. The most dangerous make-or-break point in that journey is the quiet, invisible process of just drying. Let's get into why.
So yeah, that's the big question, right? How do we get from this pliable, wet lump to a strong, useful object? Well, the answer is all about navigating this hidden minefield of forces that can literally shatter a piece before it ever even sees the inside of a kiln.
So right after it's been shaped, a ceramic piece is called a green body. And, it looks finished, but it's really just a fragile, waterlogged illusion. All that water that makes it easy to shape, that's the very same thing that makes it incredibly weak and just waiting for a disaster.
And here's our main villain, tensile stress. As that water starts to evaporate, the clay shrinks. Now, if that shrinkage happens unevenly, it creates this intense internal tug of war, a force so powerful it can literally rip the piece apart from the inside out. So in this explainer, we're going to take a journey to really understand this whole critical process. We'll start in the danger zone of drying, then get into the science of what's causing all this stress. After that, we'll learn how to navigate the drying curve, see how people actually watch the water leave, and finally, get to the good stuff, the levers you can pull to make sure everything turns out perfect.
All right, let's talk about the danger zone. We're not talking about just letting something sit out to air dry. In the world of ceramics, this is an active, really perilous stage where so much can go wrong, and it can go wrong fast. On one hand, the goal seems super simple, right? Just get the water out so you have a strong, stable object. But the reality? Well, the reality is you're in a fight against physics. If one part of your piece dries even a little bit faster than another, those internal stresses just build and build, and that leads to warping, or even worse, those catastrophic cracks. And this, right here, is the key. If you remember one thing, make it this. It is not about how fast you dry something. It's all about how evenly you do it. You can actually dry ceramics pretty quickly, but only if you can guarantee the entire piece is drying at the exact same consistent rate. So, what's really causing all this drama? Let's zoom in and look at the science. I want you to imagine a microscopic tug of war happening deep inside the clay, with the inside and the outside of the piece pulling against each other. This picture shows it perfectly. See, the surface, the outside, it always dries first. It shrinks and it hardens into this kind of rigid shell. But the inside is still wet, so when it tries to shrink a little bit later, it's pulling against that already hard shell. That's what creates all that intense internal force.
That pulling force? That's what we call tensile stress. Think about stretching a rubber band, that's tension. But here's the problem. Unlike a stretchy rubber band, a green ceramic body is brittle. It can't stretch. So when that internal pulling gets to be too much, it has only one way to relieve the pressure. It cracks.
Okay, so to get control of this whole process, we need a roadmap. And for ceramicists and engineers, that map is called the drying curve. It basically guides us through the two main stages of this whole journey.
The first leg of the journey, what you see here from point A to B, is called the constant rate period. At this point, the surface is totally saturated with water, so it just evaporates freely. This is where most of the shrinkage happens, as all those little clay particles pull closer and closer together. And this chart shows you exactly why it's called the constant rate period. If you plot the drying rate over time, you see this nice flat plateau right at the beginning. As long as water from the inside can get to the surface fast enough to keep it wet, that evaporation rate stays high and steady. Now, the switch to the next stage happens at a point called the critical moisture content. This is a huge turning point. It's the exact moment when the clay particles finally touch each other, and all that shrinkage stops. The risk of warping goes way down, but you still have to get the rest of the water out through these tiny little pores, and that's why the drying rate starts to fall off.
So the theory is great, but how do we actually apply it in the real world? We've got a roadmap, but to use it, we need to know where we are on the map at any given time. And the key to that is measurement. You can't control what you can't measure, right? So engineers have a bunch of ways to gather intel on what's happening inside the clay.
And these methods, they range from the brilliantly simple, literally just weighing the piece over time to track water loss, to the super sophisticated. You've got techniques like DTA and TGA that can spot tiny changes in weight and temperature. And then there are tests, like the defect test, that are designed to intentionally stress the clay just to see when and how it cracks.
So this machine here is a thermal gravimetric analyzer, or a TGA. By measuring the weight of a sample with incredible precision while it's being heated, scientists can build this super detailed profile of exactly how a specific clay body lets go of its water. And that data is absolutely crucial when you're designing a dryer for a big industrial process.
All right, now for the most important part, the solution. We get the problem, we know how to measure it, so what can we actually do about it? Let's get into this strategic toolkit, the levers you can actually pull to manage the drawing process.
First, let's say our mantra one more time. Dry smarter, not faster. What this really means is actively managing that moisture difference between the inside and the outside to keep that internal tensile stress below the breaking point.
And here they are, the 5 key levers. First, relative humidity. You keep the humidity high at the beginning to slow down surface evaporation and give the inside a chance to catch up. Second, airflow. You want gentle, uniform flow all around the piece, not some direct draft hitting one side. Third, green body uniformity. Consistent thickness is everything, because thick and thin spots dry at different rates. Fourth, your choice of binders. Adding the right stuff can make the green body stronger so it can resist cracking. And finally, number 5, particle size. The finer the particles in your clay, the smaller the pores, and the harder it is for water to get out, which means you have to dry it more slowly and carefully.
So as you can see, drawing is this really delicate dance, this process of controlling an invisible war happening inside the material. And as we push the boundaries of science, designing these amazing new ceramics for everything from our phones to spacecraft, we're left with this really big question. How do we master this ancient challenge for materials and shapes that we haven't even imagined yet?